And we're live. Boom. Hello and welcome to Practicalli with me, John Stevenson. Thank you very much for joining me. Today we're going to have a look at Exercism, a website that gives you a mentored approach to learning clojure. So you can go on there and do the exercises as you would do in any other website, except you can also get help specifically from mentors. So it's a bit more like an online course with actual people there to support you as well. And yeah, so let's have a look. Where's all the buttons gone today? There we go. So as usual, Practicalli website has got all my contact details and all the access to all the content that we've created, all the videos, the books I'm working on, and you can contact me via clojure in Slack on the Practicalli channel. There's also lots of really useful channels on that community there to help you out. And there's some ways you can also help support me and keep me motivated as well. So let's have a look at Exercism. So Exercism is, as we say, it's an online learning platform. And there's lots of different languages you can select from. Where are we? There we have, let's just go back to the start. No, not profiles. Come on. Tracks. Let's look at tracks. So you can choose from a whole range of different languages, and there's even Vim script as well. Whoa, an assembly language. So there's quite a range of things you can do. I've signed up to the clojure track, and if you click on that, then there's a whole range of exercises, and they're all quite small, so they're all kind of the same, I guess the same kind of amount of effort required for things like Code Wars. They're all supposed to be like teaching you something fairly specific, and if you actually do the mentored approach, then there's a curated list, so you do them in order. Here I'm using the practice approach, and I can do them in any order I want to, and I don't need to wait for any feedback. So I'm just kind of going through these as they appeal, and you can filter through difficult, like you can create a filter to find the ones you actually want quite easily. So there's about 6,000 students and 16 mentors on there. And I'm actually going to try and help out with the next version of the clojure course. They're going to update Exercism at the moment to version 3. So I'm going to try and help out, see if we can make the clojure track even better than it already is. Can I change that? Yeah, so you can see I'm in practice mode here rather than mentorship mode. I can save the time for the mentors for other people. And when you're going to use Exercism, you do need to download their Exercism tool, which installs a binary on your command line, and this just helps you get the projects. So you basically just download the projects using the Exercism tool, and you use the same tool to submit your answers as well. So we'll see that in action. And it's just helps get the executable. So it walks you through that, setting up the executable. It walks you through that, and you can also get a mentor to help you with this as well. So it also tells you how to check that something's working. And then there's a couple of things to do to configure the CLI. You set a token, and then you're ready. So setting a token, I never actually checked but I think if you go to GitHub, if I go to my account, then I am assuming that it's set up a token in where is it? It's under developer settings, I think, here. So did it set up a is it? I thought, not quite sure how that token works. It must be I must have given when I logged in. I think I gave Exercism access to my account to be able to do things. Interesting. I would have thought they'd have used a personal access token, but obviously not. There we go. I'll have a look at that to see if I can figure out what it's actually doing. Anyway, let's get on to the closure. So if you click on any of the tracks, I think Hello World is the one you start with, and you see I've already completed this, so it does track what you're actually doing. This is Hello World. I've just returned Hello World, so it gave me the code and tells me where to put the code. It even gives me a hint that I might need to update the arg list as well. And it gives me this command to be able to download the project. So I get a Leiningen project. So all the projects use at the moment, they use the Leiningen build tool, and this command downloads it. Downloads the project for you. So it downloads a specific exercise from the track. And if we go into the command line. Oops. So I've downloaded all these, so yeah, I'm just basically, let's grab one that I haven't tried yet, just to show you. Oh yes, yeah, word count, that sounds easy. Yeah, so yeah, I can download the project. Oops. So it's downloading it. In this case, it's downloading it to my projects Exercism closure directory. I did actually change that because by default it downloads it to the Exercism folder in the root of your account. But I think I did. No, it's not the one. Oh. Where was it? So it's Exercism config. Oh yeah, config workspace. So if you run that command, then you can set a specific path as to where it's going to create all your projects. So that's really useful. I didn't notice that in the documentation, but it would be useful to get that added. It's in the help if you do help on Exercism. I think it gives you different commands you can use there as well. So it's already set. Oops, sorry. Yeah, so you can configure stuff. There's a few other things you can configure. I think it's got the that's why it's setting the token it uses to upload and download things. But yeah, I don't think there was anything else I needed to do there. Oh, you can upgrade to the CLI. Okay, let's get on to the project. So I've done a few already, so we'll just briefly go through these. And if you do get any problems installing Exercism, then I'm happy to try and help. But also the mentors can try and help as well. Let's see. Okay, let's. Oh no. Exercism. So I just created a layout in Emacs for Exercism exercises, and let's see what we've got. Oops. So we started with Hello World. Oops. Hello World. So it does have a Leiningen project on there. There's nothing special in that. It's just including, it is using Clojure, well, pretty much almost the latest Clojure 1.10.0. And so I think that's what the default Leiningen template creates anyway. And it creates a source file. Oops. Without the answer, so it tells you where to put your answer, which is very handy for people just starting. And oops. And it also creates a test file as well. So you've got the source and test files, so you can go ahead and just evaluate all these, just to start the REPL, then evaluate the code and then run the tests, or you can use a command line test runner as well, yeah, it runs a test, and obviously they fail, then you look at the tests and make them pass. So I've just been looking at the tests and usually just figuring out how to make the test pass, and that seems to work okay. So nothing particularly interesting in here in terms of closure, so we'll skip on. It just does hello world. So I'm going to look at some of the other ones that we've gone through that are a bit more interesting. So we go back to the closure track. Tufer, what did that do? Oh yeah, this is just a bit of string manipulation. Oh, this is quite interesting actually. Just a brief look at Tufer. It's quite an easy one, but it's there's an interesting discussion there around whether to use a polynomic, a polymorphic function or not. So let's have a look at that. Control H. Tufer. Let's look at the source. Oops, didn't want to do that. So this is the test for it. So we've got, so basically you have to inject either somebody's name if you give it a name. So here we're getting Bob and Alice, and we're injecting Alice into the string. And if you don't give a name, then you inject a default name, which is you. So my approach really was like, well, I've got two different tracks, but they want to be the same function. So we'll do, we'll have the function respond in two different ways based on how many arguments that are given. So we've got Tufer. If there's no arguments given, we actually call Tufer again, but we inject the default string that we want to put into the final resulting string. And so then it calls itself name, and then if you do have an argument, or if you're calling it from the non-argument branch, then it's just going to return a string, injects the name into the right place, and you're done. And there were other approaches. So I did kind of like think about having this variable name, but then you have to deal with the name being in a inside a collection. So basically, when you have this @name, it can take either 0 arguments or multiple arguments, but then it puts all the arguments into a collection, and so then we have to test whether that collection is empty or not, and then also have to get that value out of the collection as well. So we're adding more code, and we're not really doing anything different. So it does seem to be a bit more verbose doing these approaches. And you could also use, instead of just getting the first name, here I've applied string over names, which would then put all the multiple names together. So if you're going to have more than one string passed into this, so if you had like 2 arguments or 3 arguments or so, then it would join them all into a string. Although we probably need to do closure string join, because you might not have any spaces between the values that you're sending as arguments, but it does work okay. And then what did I do? Oh yeah, so then I did put a condition on here as well, so just to change it up. So another way to do it is to have a let that is going to get the name, and it's either going to be the first name, or if there isn't anything in there. So if you don't press any arguments, so if you don't include any arguments when you call Tufer, then when you do first name, that's going to be nil. So it's going to be false. So it's not going. The OR is not going to do this expression, but it'll do this expression instead. So then name gets returned to gets bound to name, and then we can include that as well. So that's a nice little example of using polymorphism in a function. And the only thing we do differently is we wrap each of the arguments in as an expression. So we've got brackets around the function, whereas normally in a function we just have the square brackets. We don't have round brackets around it. But because we're going to have multiple ones, then we've got like separate branches. So these are the possible kind of routes that our code can take through this function. And if we've got 0 arguments, we take this route. And if we've got multiple arguments, we've got 1 argument, we take this route. Okay, so that's fairly simple. So let's go on to a slightly more meatier challenge. Let's see. And so once you've submitted something, you can also select that this exercise has been completed, and you can also view other people's solutions as well. What else have we got? Which one are the interesting ones to look at? I think there was some ones on, oh yeah, RNA. Yeah, let's do these two. I'm going to do RNA transcription and nucleotide count. I like the idea of biology. It's quite intriguing. So the instructions. So basically, we're given a strand of DNA, and we need to return its RNA complement. And so there's 4 nucleotides found in DNA. So there's 4 things that make up that can make up a DNA strand. So you've got A, C, G, and T. And if you convert that to RNA, which is kind of the building blocks for DNA, then you've got A, C, G, and U. So they're slightly different, but you can translate between them. And this shows how to do that. This is the mapping between DNA on the left and RNA on the right. And it gives you some background reading if you wanted to find out more about this, but to be honest, you don't really need to know anything about RNA or DNA. Just need to understand this translation that we're doing, because that's all we're trying to do. So if we go open this project in our editor, RNA, there we go. Let's open the test. Let's start with the test first. So it's all set up for us. It's including the clojure.test namespace and the namespace we're testing. And there's just a series of tests. Am I running? Let's see, I don't think I'm running that. There we go. Let's run my REPL. And so it's just doing a series of single character transformations here. So if it's if it's C, then we should get the result of G, and then there's another one where we've got multiple. We've got a string of nucleotides, and we get back the resulting string. So how have we done this? So for me, this the first thing I thought of was doing a dictionary. So you can create a map, which is like a dictionary. It's like a lookup table, or even a state transition. You can think of it as a very simple state transition as well, because we're going from the key to the value. So if we look up the key, we can find out what the value of that is, and that is what the key should be converted to. So if we have a nucleotide of G, then we should return a nucleotide of C. So it's a very easy way of doing a mapping between 2 different languages. And I've done this as a basis for for creating a simple encoder decoder. Did I keep it up there? Oh yeah, there we go. So way back in October 16, I created something called the clacks. This is based on it's kind of the Terry Pratchett book, where they've got these clacks towers, and they communicate like a telegram, like an email, but they communicate using these light patterns, and so we can create a dictionary that defines what what each of the characters in an English language, how that's represented in a light pattern. So these are lights that are either off or on, with 0 being off and 1 being on. And so I can very easily translate between 1 and its light pattern. And so if I have a collection of light patterns, then that is the encoded version of like a string or a sentence. And so I can use this map to translate a string into a series of these vectors that are, each one is representing each character in that string. And if I reverse the map, this alphabet map, then I can translate it back again. So I think that's the approach I took this time. Yeah, and so I use this very handy closure set map invert just to invert the map. So I don't have to define the map twice, which would take a lot of typing. I can just basically have this alphabet inverted, which has all the encoded on the left hand side as the key, and the characters, each individual character of the string as the values as the right hand side. So I've done the same thing in a very simple way for this. Let's do Alt. There we go. Yeah, so this is just a very simple dictionary. I only need to convert one way, so I don't need to do anything else. And so we can, if we're given the dictionary, which is dictionary DNA to RNA, and a nucleotide, so either G, C, T, or A, then we just do a get. We do a simple get. These keys are not keywords, so we can't use the keys to as a function in this case, but we can use the get function. So we want to get from the dictionary we pass in, and we're just creating this nucleotide as a string, because that's how we've got these, because we're going to be passing, just to make sure we don't pass a character. I think that's because we call convert nucleotide later on here. When we're mapping over the string, we're going to get characters. So just to make sure that we're getting a string to look up, we're forcing like a conversion between a character to a string each time, just to make sure that this lookup is going to pass. Because if we have a string and a vector, a string and a character, these are not the same. So G does not equal G, the string of G. These are two different things as Clojure understands. So we need to make sure that everything that we're using to look up is a string, because that's how these are defined in here. And if we look at the tests, so the tests are actually passing, when they're actually passing strings in here. If the tests are passing characters, then we could just use characters in the dictionary. So we'd just have these keys as characters as well. So that would work. So we could have this just take characters, but it's kind of nicer to use strings anyway, in general. Cool. And so this is quite simple. This is just taking a dictionary and a nucleotide and returning, just doing a get lookup on a map. And then the other tests were if we've got a whole string, so we need to go through each of these and look up the nucleotide and then return it as a string. So yeah, again, the first thought was to do a map. So we've got this map function here, which basically just uses an anonymous function to call, and we're using an anonymous function because we want to inject the particular dictionary into here, because convert nucleotide is taking multiple arguments. It's not just taking a single argument. So we can't just map the specific function, convert nucleotide. We have to map an anonymous function that calls convert nucleotide with a specific dictionary, and then the percent is the individual characters that we're getting from the DNA strand, as we call it. So we're calling RNA with a DNA strand, and then which is a string, and then we map over the string, and each time we call convert nucleotide dictionary with each character from that string. And the final thing that we've done here is, because there's a throw assertion error, I haven't really looked at assertion errors before and any kind of error handling before, but you can throw an error pretty much anywhere you want. There's also try catch block as well in Clojure. So if you want to wrap access to a data store or something like that, something that's not a guaranteed resource, you can put a try catch around it, and you can also throw errors specifically as well. So here we're just throwing an assertion error, which is actually just a Java error, and they do pop up in my auto-completion, so that makes it easier for them to find. And here we're just going to throw an assertion error if we've got an incorrect character in our sequence. So X is not a valid nucleotide type. So go back and look at that. So what we've done, instead of just doing a map, we've done apply string to put the map back into a string, because otherwise we just have a collection of characters. And then we've put that into the condition. So if we've got this is just basically passing the test. We could put something a bit more future-proof in here. So here we got, does a string DNA include a character that isn't part of the nucleotide? So we could do a lookup to see on the dictionary, see if the value of X, see if the string includes something that isn't one of the keys. So we could do select keys, I guess, from on the dictionary to see whether that's there, and do like it contains or something, or a sum, to see whether that character is whether, just to make sure each character is part of the valid DNA nucleotides. So make sure it's GC-TRA. And if it does include a character that's not part of the DNA, then we throw an assertion. So we're just doing is we go throw expression, and then we're creating an object, a Java object that's an assert error. So this is like instantiating a Java class of type assertion error, and that's what the dot is there for. I think you can also use the new. So we're just throwing a new object that is of type assertion error, although I think it's more idiomatic to just put the dot in there as well. So dot is just an alias for the new function. And that's it. Any questions? No? So it's quite easy to use error handling in Clojure, especially on the JVM. I haven't really looked at it in JavaScript, Clojure script yet. Let's have a look. Did I still have that open? Oh no, I didn't. Okay. We'll see another example of using a throw as well in the next exercise we're going to do. But yeah, so this could be a little bit more generic, but it passes the tests, which is the main thing. But yeah, so I would probably look to improve that checking on there to check to see if any of the any of the characters in the DNA string were not part of the dictionary, and that would be a better way, a more like a more generic way to actually solve that part of the problem. Okay, so I'm going to leave that for now and then go to another exercise. And let's go back to the closure track, and it was nucleotide count. So we're given another strand, and we need to figure out how many times each nucleotide occurs in the string, so we can kind of understand the data that's presented in a different way. So it's basically transforming data in one representation to data in another one, which is what we do an awful lot of in Clojure. So I thought I'd do this one because it's just part of the same theme. Let's switch over to my editor. Let's select the right one, nucleotide count. And so let's open the test, and there we go. So there's quite a few tests here. So we're going to do this, and I'll do a bank account to finish off as well, because that's got something interesting. So this one, again, is following the theme of the previous one. We're using DNA. But again, we don't need to understand too much about DNA. Here we can see that if we passing in, so we've got a function called count of nucleotide in strand. So how many nucleotides, how many A's and how many G's and how many T's and C's are in the string. In this case, there's going to be 0, so it's returning 0. But if there is so there's two functions. There's this count of nucleotides. So we're counting a specific nucleotide. So we just want a single integer value. So 0 if it's empty string, or if there are no instances. But if we want the counts for all of the nucleotides, then we need to return a map with the nucleotide and how many instances are in there. So those are the different ones, and if there aren't any, we still need to return the nucleotide and its value, so a value of 0 by default. Okay, let's look at the code. Oops. So I did this in quite a few different ways. So we started off with a couple of fairly basic abstractions. So I just checked to see whether it was the right kind of nucleotide. So if it's a wrong one, so there's some X nucleotides in there. And again, I could compare that with all the valid nucleotides if I wanted to. But to make the test pass, then if there is an X in there, then we just throw, in this time we're throwing the throwable object, which I think is just a more generic object from the previous error we were throwing. And so yeah, this is just instantiating a Java object again called throwable, and we've got the dot to create a new object of that type. But if it doesn't have an X in, then all we're doing is just using filter. So we're using a filter. We've created a function in line. So an anonymous function that just basically compares the nucleotide with something from the strand. So we're given a nucleotide and a strand for this function, and if it basically returns all the nucleotides that are in there. So if we call, let's do that. There we go. So if we call count of nucleotides in strands, and then we do a nucleotide, which should be, so let's do /a, and then in a strand of ACGT. Oh, there we go. Then it should filter out everything that's not an A, and it returns 1. So filter is it's just a nice abstraction, kind of an abstraction of a map really, except it just returns the things that matches this is really a predicate function we've defined here. So if something is true or false, if it's true, if the nucleotide, so if A matches something in the strand, then that's true, so it keeps the A and returns that as a value. And then all we're doing is just counting up how many A's are in there. So if we've got multiple A's, then we get 2. So that's pretty simple. Yeah. Cool. No questions on that. And then to do it for an entire strand and get all the values, first thing I thought of was using the for function. For it's actually a macro, but you can take each nucleotide in turn from a strand, and then we can just build up a map. So we're building up this map, and this map is composed of the nucleotide, so that's like the individual characters from the strings, and then the value that they're associated with is just calling count on that particular nucleotide and that particular strand. So we're just calling the function, the previous function. So that works kind of, but if we it creates this big long well, if we've got a big long string, it creates the individual maps. And because it's doing it for each character, then it's obviously it's repeating things because we've got T multiple times. So it's doing too much work in this case. So what we did was specify these valid nucleotides, and so rather than iterating over the strand, which actually could miss things, because if there isn't an A in the strand, then we're not going to get an A result here. So even if we take this big long expression and evaluate it, if we merge all those things together, we get the right answer. However, if there wasn't an A nucleotide in the strand, it wouldn't return A as a result, so it wouldn't be the right result. Let's just copy this. Like that. So I've defined again another kind of lookup table. Here we're just having the valid nucleotides, so we can use that to iterate over instead of the strand. So here we're just iterating over the valid nucleotides, which does stops any redundant work happening, but it still produces the individual maps for each nucleotide, so we still need to merge those together. And because it returns them as a collection, as a sequence, then we need to apply merge to flatten, to basically flatten the results that we get. But that does work, although it's not necessarily the most efficient way to do things in this case. We're also using a macro as well, so it does mean that this is slightly less composable in some situations. So can we do it without a macro? Well, we can just use a map function. So here we're going to map our own custom function over the valid nucleotides, and this is just it's kind of doing the essentials of what the for loop is doing anyway, because we're kind of iterating over our 4 valid nucleotides, and it's going to create a map here, and the map is going to be consistent of a nucleotide, and then getting the count of that nucleotide from the string. So it's going to do this call 4 times and return it, return a map. However, we still need to do the apply merge because we're still generating individual results there. So we're just putting this map in here instead of the for function, and applying merge just to make a flattened result. So those work, and although they do give it, they're quite still quite verbose, and that's when I remembered a magic function called frequencies, which kind of does all this for you, which is very nice. Oops, wrong button. There we go. Let's just comment these out. There we go. Whee. Keep that for now. So frequencies, what does that do? Frequencies is really handy. So I've used this before to basically see how many times something, so each character in this string is going to appear. So if we evaluate this, then we're getting a, let's do that again on there. So we're getting a map back already. So it's doing all the work for us. So we don't need to do any of the map. We don't need to write our own function. It actually is doing all this work for us straight out of the box. So that's a nice refactoring to make the code much more simpler. So it's just going to go through all these and find all the A's, find all the G's, find all the C's and T's, and return it into a nice map. So that's really handy. So we can simplify, we can simplify both of these functions actually. So I went back to the define count of nucleotide in strand. So this is the first function we did, and we can just use frequencies, the strand, and that's going to return the map above. And then we could just get the particular nucleotide we actually want from that map. So that's a fairly simple piece of code. And it's quite straightforward, I think. And then we need to, but we still need to add the error exception that we did before. So if we look at here, we still need to add this throwable in here. So, which we don't have here yet. So we've refactored that count of nucleotides in strand function. And what I tried to do was I tried to be really clever because you've got in the get function. So if you get something from a map and it's not there, then you can specify a particular not found result. So if I do this, then we get, oh, so A is not inside this map. Well, there's nothing inside the map, so it can't find this. So this result of getting A from the map is false. So then it'll return a default value, which is really handy. So I tried to do that with throw, but obviously this expression will go and evaluate. So the get expression will go and evaluate the throwable expression before it evaluates the get, because it's a nested expression, so it needs to know what the value of that is. And so then what it does is just throws the throwable. So that kind of throws an exception straight away before it actually does the actual get lookup. So it can't quite do that approach. So that's something to fix. And also, if there's an empty value, I actually want to return a 0 rather than returning nil or returning nothing. So I put this if statement around it. So if empty, let's comment that. So if the strand is empty, then we can actually just return 0. We don't need to do any other work. And so if there's nothing in the strand, which is one of the tests. Oops. If we look at the tests, one of these strands, yeah, so it's an empty strand, so we need to return 0 in that case. So we added that in here, but then we still need to fix the throwable. Because if we do, let's just evaluate this. So that's the function running. So we got, we're just doing a get on the frequencies, and if the nucleotide is not there, then we should throw the throwable. But because we're evaluating the throwable straight away, we get a oops. Oh, sorry. Oops. Ooh, I've broken it. Oh, there we go. We get a Java lang throwable, even though B is in the map, because throwable is being evaluated before we actually do the get. So, and then throwable is an error, so it stops everything else from happening, which is a bit tricky. Yeah, I tried to wrap this whole thing. I tried to put in a quote and the hash quote as well. Oops, the reader quote. But it didn't like it. So I can get it. If you do the quote, then it's going to it kind of does work. But then when it's an error, it's not returning. Oops. Oh, I didn't want to do that. It kind of returns the expression, but it's not evaluating it. That doesn't quite work. So I couldn't quite find a way to actually get the throwable result from there, just by including that, because it kind of does expect that to just be a value. It's not really a function there. Although if the function just returns a value, then that's going to work okay as well. So I did ask the audience, and the audience just suggested using OR instead, which is kind of seems quite obvious once somebody had mentioned it. But yeah, so if frequencies doesn't find anything, so if this part of the expression doesn't return anything, so if it tries to look up the nucleotide and it's not there, we get nil, so that's like false. So then we'll do throwable. So it's kind of delaying the evaluation to throwable, but still evaluating it if it needs to, because if we because using the OR, it will read it, and it will read this first expression and evaluate that expression first, and then if that returns nil, then we'll do a throwable. If we put these two expressions the other way around, then it would be the same as doing the get as well, so it would always throw the throwable before it did that. But this one kind of works okay. So if we do so that's how we got round that one, and it keeps the, I mean, the reason I wanted to put throwable in there was just to keep it nice and simple in terms of the expression, keep it quite obvious what it was doing. And I think the OR macro does that quite nicely. So you either do the get frequencies, and if that's nil, if that's false, then you do throwable. Yeah, it was really really obvious when somebody else pointed it out. Yes. Okay, so that's the nucleotide in a strand. I think that's the version I went through. And then there was the nucleotide count, which I looked at again with frequencies. So this really simplifies it down. If we look at the original one we had, then they're doing this for loop and applying, merging, and that sort of stuff, which is quite complex. And we could just replace all that with frequencies strand. The only problem with this is that if we do this, it doesn't actually generate the values. So if we do nucleotide count and we pass it in a string with just GGG. Oh, did I break it? I've broken something. Ooh. Oh, we can't find the... Did I spell that wrong? I must have spelled it wrong. Oh, it's counts. Oops. My autocomplete fail. Oops. Oh, okay. Oops, there's two there. I selected the wrong one. Helps when you call the right function. There we go. Yeah, so if I do nucleotide counts and there aren't any strands of A, then I'm not going to get the right result. So thinking back to the merge that we were doing, well, we can just actually start off with a starting condition. So we can start off with a map saying, well, okay, they're all empty. We haven't found any yet. And then we do frequencies. And then we can merge the results of frequencies on top of the starting condition, which is all 0. And then we can merge them together. So we can merge the results of frequencies onto our base case map. And that works. So we've got that one and that one. Oops. And if we evaluate all these, then they all work. So all the tests pass. We've got green across the board, and then I just submitted the results. So we get two pretty simple things there, and I wonder. Yeah. So this is far more reduced than the for or even the map solution, because we're using frequencies to again extract exactly what those things are doing. And then have we got time? I think we've got time for one more. Squeeze one more in. So I did. Was it bank account? I think it was. Oh yeah, I did bank account. Which says it's medium. I guess it's medium because you need to know. It sounds quite complicated. Basically, you have to do bank account withdrawals and supports. Is there a convention where to put tests? So far on these exercises, then there's only been one test namespace. So we have a look here. So there's one namespace for the source code and space. I'm just switching to the test file, and then there's a parallel test file here as well. So it's the namespace of the namespace we're testing with the dash test on the end, and we're pulling in the nucleotide count. That's the namespace under test, and all the tests are going in here as well. So you don't need to, and that's all set up for you as well when you actually download the project. If we just switch back to here, so if I have a look at bank account, and if I have a look at the tree structure, so this is everything that's created for you. I mean, the target's being generated when I've been compiling things, but you've got the source code branch that's already there, and you've got the test branch as well. So it's usual kind of Leiningen clojure approach to structuring a project. The only difference if you're using clojure-cli tools and deps.edn, the only difference is you'd have a deps.edn file instead of, or even as well as the project.clj file. If you have multiple namespaces in here, you would create an equivalent namespace for each of the namespaces in source under test. Hopefully that answers the question. Let's just switch back to this. That's not right. So let's open bank account. Let's open the test. Bank account test. So this is the only problem I had with this is that when I run the tests in Cider, it just died completely, just actually killed the REPL each time, which is not good. But it worked. It worked when I submitted it back to the Exercism. It all worked. And so basically, there's open bank account and get balance. There's also an update, and I think there's a close account as well, so we can close the account. So there's 4 kind of things, but these things might happen in parallel. So it might try and do some concurrency on you to try and kind of update multiple open bank accounts and update them with different balances. So you kind of have to manage that. And so I guess that's the trickiest part. Everything else is pretty simple in this one. So how do we manage that? How do we manage the bank accounts? Let's just sorry. And the bank accounts are is just returning values each time, but that value is associated with the particular account. So we need some way to uniquely represent the accounts, and so in this case it's doing a threading macro. So it's going to call bank account open account, and then it's going to get balance. But get balance is going to have an argument passed to it from the result of this. So if we return the bank account ID from this expression, then we can pass that into the get balance, and it will return the bank account value for that particular account. So this is a bit like calling this, and boop. If we're doing it Lisp style, then it'd be like doing that. So the get balance has an argument of open account, which if that returns an account ID, then we can just do a simple lookup, and so that made me think, okay, well, this is probably a map that we need. So we can have a map that contains all the bank account IDs, and for each ID, then we've got a balance. So that's what I did. Yeah, so how I've created an account. So when we open an account, it doesn't take any arguments in the tests, so we don't have any arguments in the function we've written. But what we're doing is we're going to generate a random universal ID, and this really handy kind of Java util function called random UID, which will generate a random ID for us. And so they're pretty unique. I think you have to generate billions of those before you have to worry about getting them the same, because it's also based on time that you generate them as well. So we get a unique ID, and then we can just associate with that ID. So we're doing an association on the map, and we're putting account ID in there with the value of 0. And then we're using a let because we want to return the account ID from that. And so we're having to use a swap because I decided to put everything into an atom. So an atom is just a container, a box, which you can swap values in and out of. You can reset the box. So the box itself is mutable. Oh, mutable. But we like immutable things in Clojure. So how does that work? Well, the things you put inside the box are still immutable. They're still not. We're not changing the. Yes, we need STM for this. Yes, so we're not changing the values that we put in the box, but we're changing what the box contains. So that's something that confused me at first, because I thought, well, if we're putting everything in atom and now making everything mutable, then that's going to just cause chaos. But actually no, because the things we're putting in, the things we're swapping in and out of the box themselves are still immutable. It's the box that's mutable. So it's like having a different view on the current state of something, and we can update the state, but we're still using we're still using immutable values, so we're not kind of adding extra complexity. And we can use if we use the atom, then actually Clojure takes care of putting the values in and making sure that multiple things queue up in order to update the atom. So we don't have to worry about locking the atom, and we can think of the atom as like a very, very simple in-memory database that we're putting things in, but Clojure is going to manage all that for us. And here we just start off with an atom which is empty, but basically it's going to have the shape of account ID, UUID, and then whatever value. So we'll start with 0, and then somebody can pass in the relevant account ID, and they can go off and get the value that's associated with that. So again, it just turns it into a very simple lookup of a map, as we've been doing in other examples. So when we open an account, we get our account ID back, and we swap in the value into bank accounts, which is what the atom is called. The atom is called bank accounts. So we swap the value that's already in bank accounts, which is just the empty map, and we do an associate on the map, and we put account ID in there with the value 0. So to close the account is very simple. If we've got the account ID, then we just disassociate that ID from that, and it's just dropping the account ID from the map, and we get a new map with the same values except for that ID. So that just closes the account, and I don't think it needed to do anything. Yeah, when it closes the account, yeah, it just returns a nil. So if you do a get and there's no ID, if there's no account ID there, then the normal get function returns a nil there anyway. So we don't need to do any error handling there at all. So that's pretty simple. If we want to do the get balance, the only thing we have to do is respect the fact that we're dealing with an atom rather than just a map. So if this wasn't an atom and just a map, then we just have bank accounts, and we just do get bank accounts, and then the value that's the key that we're looking up, in this case the account ID. But because it's an atom and it's this special box that we're putting things in, we need to dereference it so we can actually go and talk to the map rather than the atom. So that's what this @ sign does. It says, well, I want to talk to the thing that's in the atom, not the atom itself. And this @ sign is just a shortcut for this deref function. So bank accounts. There we go. So we do deref bank accounts, then it will return the map, the current map that's inside the atom. So the deref and the @ sign is the same, although I think I very rarely see deref. Again, most people use the @ symbol in there. Oops, wrong buttons. There we go. And and then there's updates. Oh yeah, there's update. Here we go. Update balance. So the account's already there because they're always creating the account. So we don't need to do any checks to see whether the account exists or not. So we've given an account ID and some credit, and the credit is either going to be plus or minus. So if it's taking away, then we're just updating the account with minus $10 or £10. If we're adding to the account, then we're giving it like a £10 addition, and we can simply just update the account ID with a function. So we're going to look up in the map. So we've got our map, which is bank accounts, and inside a swap, it automatically dereferences the bank accounts, thing, because it knows, swap knows it's going to be dealing with an atom. In fact, you have to use swap in order to update an atom, or you have to use swap or reset to change the values in an atom. So you can't go and just change the values by doing a normal update or ASOC. You have to do it inside a swap, because it's the map itself is inside the atom. So we're swapping into bank accounts, and we're going to change the account ID by doing an update. So we're going to update the existing key, whatever that is, that UUID, and we're going to do an update by using a function. So we're basing the new value is going to be based on the old value with this function applied. So we have this function, this inline function we've defined, and what it does is it adds the percent is going to be the current value. So bank accounts, so the swap function update will go and get the current value for this ID and put it into our function, which is where the percent is. And so we have our, so if our account is 0, so this would be 0, and we would add the credit to the account value, and then the atom would have a map with the new value in there, and we're done. So if we have, can we do this? Yep. Oh, here we go. It's got some working outs. So if we open an account and get the balance, we get 0. And if we dereference the bank accounts, we actually get this UUID. Let's just comment that out. Oh no, I want that. We get this UUID. So this is what the UUID generates. So it's got a unique value. Oops, that's not right. So it generates this unique string value, which is the ID itself. But it also adds this hash UUID on it. So this is like a tag. This is like a little label, a bit of metadata it sticks on there. So it just tells the Clojure reader that the next thing is going to be of the form, or the next thing should be of the form of a UUID, which has a specific structure. So this is, although this is a string, because this string has a label of UUID, it's saying to Clojure that this string should be of a particular shape. So it's a nice simple way to add a bit of checking, so you can't create a bad UUID. It can't be of the wrong shape if you've got this label, because Clojure will pick that up. And so if we update the balance, we can pass it in the UUID with the value, and then that makes the we go from 0 to 10. And if we do if we pass a -10 value, then obviously it's going to, this value would be 10 in here, and then we would have a credit of -10. So when we add add -10 to 10, then we get 0 again. And that's it. I never did figure out why the test runner inside crashed, but when I submitted this to Exercism, it all worked. Let's go back to there. So that was my solution that I put in there. It all works. So when you submit something, it all kind of works. And to submit something, which I don't think I showed you, is so we can do Exercism. Submit, and you can just specify that here we can just specify source bank account, and it goes off and submits it, and you can go and look at the result. There we go, and there is, oh yeah, and you can go and look at the community solutions there as well. The one thing I'm not quite keen on is you have to actually go and look at, there's no list of all the solutions in here, I guess because they're quite long, so you have to go and look at the individual ones. So you never quite know what you're actually going to get. So look, as an atom, there we go. Oh yeah, that's interesting. So here, the close account, we could just reset the account to nil. So we could just reset a particular ID. So that's a different approach to. So I've just removed that account from my atom. Oh, I think he's using just a value in there. Interesting. Oh, there we go. But I haven't. Oh, interesting. Open false. Oh, okay. Here we're using a kind of a flag on the map, so it's got. Oh, okay, yeah. So we can have some history in here. So we've got open true, open false, the amount. Interesting. So we could have like account ID and the amount. Interesting. Yeah, because if you want to, in a normal bank account, you would need to keep the account around. Even if you closed it, you need to keep the history of the bank account around. So just disassociating things is a bit of a brutal approach, unless you've got some kind of history in a different system. But yeah, I think that's all the ones I'm going to do. Oh yes, we're over time now. So there's about 76 exercises. We're also going through a review of the closure track as well. And so I'm going to finish off doing some of these more challenges, see if there's more interesting stuff. But we're also reviewing the whole closure track and making improvements as well. So if you see anything you think's more complex or things that would be missing from this closure track, then please let me know, and we'll see if we can get them added. Okay, I'm going to leave it there. So again, if you need to get in touch with me, then let's go to Practicalli, practical.li or practicalli.github.io, and reach out to me via Clojure in Slack, and go and see my books as well. I've done some more work on the Spacemax book, and hopefully in the next few weeks I'll do some more work on the Clojure book as well. Okay, no more questions. Okay, I'm going to leave it there. Thank you very much for listening, and I'm going to enjoy the rest of the Sunday. Hope you do too. Thank you very much for joining me, and see you next time. Bye-bye.